If you're a last minute Jamb UTME candidate, I can help you. I can help you even if you have not been studying, you have not been preparing, your preparation has been weak. So I can help you. I can help you pass your Jamb UTME. All you need is my sharp plan. My sharp plan for 9 minutes preparation. That's all you need. Access all my lesson notes. They are very short, straight to the point. That's what you can see on the screen. So access them, access my sharp plan. My sharp plan for 9 minutes preparation, for last minute preparation, guarantees you 70 marks in English, 60 marks in physics, and 60 marks in chemistry. Worst comes to worst. I'm telling you. So all you have to do to get this plan, and I will force you to pass Jamb UTME, all you have to do, send me a DM. How will you get my phone number? Go to my profile or my bio there, my phone number, just stay there, add and send me a DM. Tell me that you need the sharp plan or you need my concise and short lesson notes to pass your Jamb UTME. I get many things, why would they help you? I've been doing this for more than 4 years now. So grab this opportunity before it passes you by. Don't let 2026 to pass you by. Pass this Jamb and enter university this Jamb 2026. I don't want you to sit at home and continue doing home shots. Another 1 year again. 1 year is such a long time. So Jamb UTME candidates 2026. Take action. I welcome you to today's lesson continuation. Alright. Today we are looking at force on conductors in magnetic field. Force on conductors in magnetic field. So the force between conductors. Parallel current attracts. Okay. If the current is parallel, like this, it attracts. When it attracts, it moves in the same direction. So if the current is parallel, the current attracts. Alright. And it moves in the same direction. But it repels when the what? When the position is opposite. Alright. When the position of the current is opposite. So there is repulsion when the position of the current is opposite. And it is given by this. The relation is given by this. Alright. F, which is the force, is equal to this naught. Current 1 times current 2 times length over 2 pi d, which is d is for the distance. Alright. So force on charge, F is equal to quantity times what? V times B. Okay, sine theta. And the current on the charge is measured with a what? A Fleming's left-hand rule. This is what you have to take seriously here. So forget about these Yamayama formulas we full here. Okay, they are just here to confuse you. Okay, now why Jamb put them for there to confuse you? Leave all this formula. Don't invest for all this kind of thing. Now frivolous investment. All right. So what you have to know is the force on a charge is measured with what? A left-hand rule. Fleming left-hand rule. Right-hand rule be like this. Right hand. This one a left-hand rule. All right. We are going to look at the Fleming left-hand rule very soon. All right. So the DC motor, direct current motor, current in coil rotates in field. All right. Current in the coil rotates in the field. The magnetic field formed. Okay, that's how the DC motor works. That's how it rotates. Okay, current in the coil rotates in the field. All right, the magnetic field formed. All right. So electromagnets. How does electromagnets work? So electromagnets work under the principle that an electric current produces a magnetic field. That's how the solenoid works. I gave you an example when I explained solenoid. Okay, when you induce electromagnetism is inducing current into a system, and that current in turn forms a magnetic field that brings about mechanical energy or rotation, motion. All right. So we induce current into the system, and the current creates a magnetic field around the conductor, and it brings about motion. Okay, so that's how electromagnets work. Okay, so electromagnets are used to induce motion or mechanical energy by the application of current. So when you apply current on them, they form or they induce mechanical energy, motion. All right, so it's used in Motorola's electric motors like this one now, electric motors. All right, and use it where mechanical energies are required. All right, alternator, you see the user. So what are the uses of electromagnets? You use it in cranes. Okay, use it in relay, use it in electric motors, use it in generators. Okay, so these are the uses. Put on for head for crane. This crane, what they use for? You know the kind of crane? What kind of crane? It is used in magnetic cranes. All right, magnetic crane, where magnetic field is used to lift objects. Okay, a magnetic crane, relays. Okay, use it in relay. You know what relay does now? Relay is it facilitates the movement of, you know, currents, or depending, is it current or magnetic field, depending on what is required. All right, electric motor, I already explained it to you, and generators, generators, electromagnets for what? Generators. Do you recall the dynamo generator? But this is true contact. True contact. All right, true contact, whereby electric field is formed from the belt of when the belt moves around the wheel of the generator, dynamo generator. You can as well look that up. Okay, dynamo generator. It is not related to magnetic field, but just look that up. Dynamo generator. All right. The strength of the electromagnets depend on these three determinants. The first is the amount of current flowing through the coil. The strength is determined by the amount of current flowing through the coil. Okay. The second is the number of turns in the coil. The third is the nature of the coil material. Okay. So the current flowing through the coil, the number of turns in the coil, the nature of the core material. Okay. What is the core made of? Is it made of soft iron core? Is it made of hard iron core? Is it made of aluminium core? What kind of core? That's what is going to determine the strength of the electromagnet. Okay, so when you have more turns, it's going to have stronger electromagnets. It's going to produce a stronger field. Okay, and bring about a stronger motion. Okay, so when you have more current flowing through the electromagnet, you are going to have a stronger magnetic field and what? A better or stronger motion. When you use a good material, a quality material such as soft iron core to manufacture the core, okay, the magnetic core, you are going to get a stronger, you know, magnetic field and a stronger motion. All right. The carbon microphone. The carbon microphone. In the carbon microphone, there's a principle at which this carbon microphone functions. A functions when sound wave is transmitted, then this sound wave enters the diaphragm, and as it enters the diaphragm of the carbon microphone, it moves the diaphragm. And as it moves the diaphragm of the microphone, it brings about a resistance change in the carbon granules. And as the resistance changes, resistance now, resistance of, the sound wave transmitted, okay? And as the resistance changes, it brings about a current variation. When there's change in resistance, there's a change in current. And that brings about the reception of the sound wave as electrical impulse or as electrical energy, all right? So this is the conversion of sound wave to electrical energy. And an electronic device is going to detect this sound wave as sound, all right? So that's when you use the carbon microphone to talk. As you talk on the carbon microphone, it sends sound wave into the diaphragm of the mic, okay? And that sound wave sent into the diaphragm of the mic leads to the vibration or the movement of the diaphragm. And it brings about a change in resistance in the carbon granules found in that diaphragm. And that in turn brings a current variation, which is interpreted by an electronic device as sound, okay? That's how the carbon microphone functions, all right? Now we are looking at the instruments, various instruments used to measure currents, all right? We have two major types of instruments used to measure currents. The first one we have here is the moving coil instrument and the moving iron instrument, all right? Most of the time, this moving iron instrument is the hot wire instrument, all right? But the moving coil instrument, most of the time, they are usually galvanometers and what have you, all right? So for the moving coil instruments, they are usually sensitive. For example, you have a moving coil galvanometer, you have voltmeter, all right? So for the moving coil instrument, it has a moving coil, a coil that is moving, all right? So they are sensitive, okay? What it means that they are sensitive is that they easily detect currents, no matter how small the current is, okay? So for voltmeters, it is used for what? Voltmeters. So you use moving coil instruments together with voltmeters, all right? That's how voltmeters are formed, all right? Moving coil instrument is part of voltmeter, okay? It's part of voltmeter. It's part of the parts of voltmeter, all right? So they are usually sensitive. Moving iron instruments, such as hot wire instruments, hot wire ammeter or hot iron ammeter, they are robust. They are what? Robust. They are more robust than the moving coil instruments. Remember, moving coil instrument, you have moving coil galvanometer and you have voltmeter, all right? And here, they are robust. They are more advanced than the moving coil instruments. Hot wire instruments or moving iron instruments are more advanced than the moving coil instruments, okay? And they are used for ammeters. They are parts of the ammeters, all right? So, moving coil instruments for voltmeters. Moving iron instruments for ammeters. Don't forget to... So, there are ways we convert galvanometer. You can convert galvanometer to various types of instruments, all right? For example, we can convert galvanometer to ammeter. And what do we have to do to convert galvanometer to ammeter? All we have to do is to shunt the parallel connection, and it turns to what? To ammeter. Okay? So to convert galvanometer to voltmeter, what do you have to do? It's easy. Use multiplier series. Very easy. So to convert galvanometer to ammeter, you shunt the parallel connection. While to convert galvanometer to what? Voltmeter, you use multiplier series. Very easy. So the sensitivity. What influences sensitivity? Sensitivity is high for low current deflection. For low current deflection, sensitivity is high. So low resistance, strong magnet. So if you want sensitivity to be high, you need a low resistance and you need a strong magnet. All right. So when a wire is big, for example, okay, you know that a big wire has a high resistance. Okay. So when a big wire has a high resistance, it's going to reduce sensitivity of the wire to current. It's as simple as that because the resistance is high. So when you reduce the resistance, a thin wire it will be very sharp. A thin wire will have a high sensitivity. That's it. So you reduce the resistance and you bring about a strong magnetic field, and the sensitivity of these instruments, this moving coil instrument or moving iron instruments will be high. That's how to increase the sensitivity of the instruments. Just bring about a strong magnetic field, add a strong magnetic field, and lower the resistance of the conductor in the instruments, and sensitivity will high. If you want to lower the sensitivity, increase the resistance of the conductors in the system, and give it a weak magnetic field, and watch the sensitivity fall. Let's look at the difference between moving iron instruments and moving coil instruments. Jamb said you should know all this, all right? For moving iron instruments, it works on attraction/repulsion of iron in magnetic field. Like pole repair or like pole attract. That is how the moving iron instrument works. So it measures alternating current and direct current. So the moving iron instrument measures both alternating current and direct current. It has a non-linear scale. That's the scale is not straight. It's not straightforward. Okay, it has a non-linear scale. And it is rugged but less accurate. It is rugged, it means that it is robust, it is advanced, but it is less accurate. Why is it less accurate? Because it is not so sensitive, all right? Now, let's look at the moving coil instrument, all right? For the moving coil instrument, it works on current carrying coil. It works on a current carrying coil in a permanent magnetic field, all right? It works on what? A current carrying coil in a permanent magnetic field, all right? So, what is it used for? It is used to measure direct current only. So, for the moving coil instrument, it measures only direct current. So you can see why the moving iron instrument is more robust. You can see why the moving iron instrument is more rugged than the moving coil instrument. The moving iron measures both AC and DC. The moving coil instrument only measure DC, direct current. All right. So it needs rectifier for AC. So if you want to use it to measure alternating current, you will need a rectifier. Okay, so this rectifier is found in alternators. Okay, they are used to convert direct current to alternating current. Okay, that's the function of rectifier. Put that in your head. It is found in alternators, used to what? To convert direct current to alternating current. So if you want to use moving coil instruments to measure alternating current, you will need a rectifier to convert it to alternating current. Okay, to convert direct current to alternating current. And the moving coil instrument has a linear scale. It is more sensitive and precise, but delicate. That's it gets spoiled easily. Any small thing, you don't get fault. Okay, it's very delicate. Any small thing, you don't get fault. Okay, more sensitive. It has a linear scale, straight scale, easy. You can use it to measure easily. It's not like the moving iron instrument that is less accurate, and it has because it has a non-linear scale. The scale is not straight. You have like a scale now just from 0 to 100. That's a linear scale. But for moving iron instruments, you will need calibration. Oh, the scale is not linear. You will need calibration. If you are talking about the most advanced out of the two, go for what? Moving iron. If you are talking about the most sensitive, go for moving coil. How does direct current motor work? How does direct current motors work? The principle. Current is transmitted into the field, a magnetic field. All right. Current is transmitted into a magnetic field, and it brings about a force. That's how direct current motor works. Direct current is induced into a magnetic field, and it brings about motion, rotation, force. Okay. And it is detected with a Fleming's left-hand rule. Okay. The force is detected. This force is detected with a Fleming's what? Left-hand rule. That's like this. Where is the force in a Fleming's left-hand rule? This is a Fleming's left-hand rule. Where do you have the force? Find it there. This is the force, the thumb, okay, represent the force, okay. So this is the force, brings about the rotation, okay. This is the direction of the current, this long finger, the direction of the current, this one for fuck you, okay. Why this one, okay, is the magnetic field. So what are the parts of the direct current motor? The parts include an armature, a commutator. The commutator is a split ring. Remember, in direct current, when direct current is to be formed, or anything that concerns direct current, you use split ring, okay. That's the kind of commutator used. Jamb set this question last year. They set this question last year, asking the kind of something a generator company wanted to manufacture a direct current generator, but they mistakenly manufactured a alternating current generator. What should the generator company do? They brought change split ring to slip ring, change split ring to slip ring. So this one now you have to get accustomed to this now. Split ring is when direct current is to be produced. That's when you use a split ring commutator. All right, split for direct current, slip for alternating current. So slip is for alternating current, split is for direct current. So among the parts of the direct current motor, you have the brushes, okay, you have the field magnets that creates the magnetic fields. So these are the primary components of the direct current motor. So how does it work? How does the direct current motor work? You put direct current, you induce direct current into the system, and the direct current brings about the rotation of the coil, all right. And as the coil rotates, the commutator keeps rotation one way. This commutator, this split ring, help the rotation to be in one direction. It's not going to start rolling like this, okay. It puts it in one direction. So that's the function of this split ring or the commutator, to ensure that the rotation or the motion or the force is in one way. All right. So what is the function of this direct current electric motor? Okay, the direct current motor, what's the function? It converts electrical energy, which is the direct current, to mechanical energy, which is the what? The force or the motion. Easy peasy. Now that we have understood direct current motors and magnetic field, the force induced by magnetic field through the induction of current, let's take some Jamb must repeat question to test the knowledge we've acquired so far and measure our readiness, how ready we are for the Jamb UTME 2026. Jamb must repeat questions. Question 202. Force on current carrying conductor uses what? A. Fleming's right hand rule. B. Left hand rule. C. Ampere's law. D. Ohm's law. What's the answer? You know the answer, right? Drop the answer in the comment section. Question 203. Parallel current attracts if A. Same direction. B. Opposite direction. C. Perpendicular. D. No current. What's the answer? Drop the answer in the comment section. Question 204. DC motor works on A. Electromagnetic induction. B. Force on conductor. C. Heating effect. D. Capacitance. What's the answer? I know you know the answer. You know book now. Drop the answer in the comments. Question 205. Electromagnet strength increases with what? A. Fewer turns. B. Higher currents. C. Weaker coils. D. Lower voltage. What's the answer? You know the answer, right? Drop the answer in the comment section. Question 206. Galvanometer to ammeter uses what? A. Series resistor. B. Parallel shunt. C. Capacitor. D. Inductor. What's the answer? It's asking you that converting a galvanometer to an ammeter, what should you do? What should you use? All right? Drop the answer in the comment section. I know you are a scholar. Drop the answer in the comment section.